What happens when a star ventures too close to a black hole? In 2020, astronomers caught an actual black hole eating a star. It's not often that we get to watch these events unfold, but this time they were prepared and managed to capture this spectacular view of matter. Being pulled apart by one of the most extreme phenomena in the universe, this is the first time that we've seen something like this happen, so let's take a closer look at what exactly they saw. This video will be divided into 3 sections. First, we'll examine the star's journey into the black hole's grasp. Then we'll see how it was ripped to shreds, and finally, what happened after it disappeared beyond the event horizon. Let's start with a brief introduction to black holes. A black hole is a region of space from which nothing can escape. It has a radius known as the Schwarzschild radius. If you venture inside this boundary, commonly known as the event horizon, then there's no turning back. Not even light can escape a black hole's gravitational pull. Once it crosses the event horizon, the only thing that can happen is that you fall further and further into the black hole until you reach the singularity. Here, all matter is crushed together at a single point, and our current understanding of physics breaks down. The real-life black hole that ate the star is known as HR 6819. It's located around 10,000 light-years away in the constellation Valens. It's otherwise known as the Flying Fish. In October 2020, astronomers noticed that something strange was happening. A bright flare had been detected from this particular system. First, they thought that perhaps 2 stars had collided. But the following month, when they checked up on it again, they found that the light was still there. And that's when they realized that something unusual was going on. In February 2021, a team of astronomers led by astrophysicist Karen Marsh of the University of the Red Sea in Saudi Arabia started observing the system closely. What they were witnessing was a binary system consisting of a neutron star and a red giant star. The neutron star was small but incredibly dense, while the red giant was massive, around 10 times larger than our Sun. Every 40 days or so, part of the red giant would dip in and out of sight behind its companion star. Each time it did so, it caused a bright flare of light to be released. This was giving the astronomers clues about what was happening. They were watching a black hole feed on a star, and they were watching it in real time. Over the next few months, the team continued to observe the star as it made its way towards the black hole. The gravitational forces generated by the black hole tore the star apart in a process known as spaghettification. This is what astronomers witnessed during the 5th orbit of the doomed star. That est, when the material of the red giant began to stretch and thin as it approached the event horizon. The intense gravity of the black hole literally pulled it into a long, thin noodle shape. By the end of the 15th orbit, half of the star had already vanished into the black hole. By the 21st orbit, the star was completely gone. But astronomers didn't stop observing this system even after the star disappeared from sight. Why? Because they knew that something interesting was about to happen. As the material from the star continued to spiral into the black hole, it heated up to millions of degrees Celsius. At such high temperatures, elements heavier than iron are forged in the intense heat and pressure. These elements are then released into space at incredible speeds, allowing us to detect them here on Earth using special telescopes. Astronomers call this a kilonova. It's similar to a supernova explosion. But instead, it comes from the merger of 2 neutron stars, or a neutron star and a black hole. After more than 6 months of observation, the team finally witnessed the kilonova. The material from the red giant that had been held up by the intense gravity of the black hole was now being released into space. This material included heavy elements such as gold, platinum, and uranium. To understand just how rare of an event this was, let me tell you this. All the gold in the entire Earth could fit into a cube that was just 60 centimeters wide. That's how dense gold is. And yet every year, neutron star mergers produce enough of this precious metal to fill up 10 billion of those little cubes. So if that doesn't blow your mind, I don't know what will. And here's another crazy fact. The kilonova was visible to the naked eye. Well, sort of. Here's what I mean. When this event occurred, the sky would have appeared brighter than a full moon. Unfortunately, the kilonova only lasted for about 2 weeks before fading away. It was still visible for a couple of months after that, but it required a telescope to see it. and it was until 7 months after the original flare that the kilonova was finally recognized for what it was. During this time, the material that had been released from the star formed an accretion disk around the black hole. An accretion disk is a structure made up of glowing hot gas and dust that surrounds a black hole. As the material falls into the black hole, it heats up to millions of degrees. During this process, some of the material is flung outwards, forming the accretion disk. This material can travel at incredible speeds, reaching almost 30% of the speed of light. Once it reaches the edge of the disk, it begins to rain down onto the black hole, releasing huge amounts of energy. It's this energy that makes accretion disks such fascinating objects to study. By observing them, we can learn more about the black holes themselves. For example, in this case, the size of the accretion disk allowed scientists to work out the Schwarzschild radius of the black hole. And with that, they were able to determine the mass of the black hole. The team discovered that the black hole was around 10 times more massive than our Sun. The question is, where did this black hole come from? Well, it's possible that it formed from the remnants of a massive star that went supernova. Or perhaps it was created when two neutron stars merged together. More research is needed to say for sure. Black holes are some of the most mysterious objects in the universe. They can be incredibly difficult to detect, since they do unemit any light or other electromagnetic radiation that we can see. However, we do know that they exist because of their gravitational effects on nearby matter. For example, stars that orbit near a black hole appear to move faster than expected. And as matter falls into a black hole, it heats up and emits X-rays that we can detect. To date, scientists have found several supermassive black holes at the centers of galaxies. One of the best known is the supermassive black hole at the center of the Milky Way, which has a mass of around 4 million suns. Despite their enormous size, black holes are still very difficult to study because they're so far away. Most of the observations we've made of them have been of light that has been bent or distorted by the gravity of the black hole. However, this also means that black holes can act like natural telescopes, allowing us to see very distant objects that would otherwise be too faint to see. This is because the gravity of the black hole bends light in such a way that it magnifies and distorts the image of whatever is behind it. By studying these distorted images, astronomers can learn more about the black hole itself, as well as the objects that are near it. Another technique that astronomers use to study black holes is called gravitational lensing. This involves looking for the gravitational effects that black holes have on other objects in their vicinity. For example, in 2019, astronomers discovered a quasar that appeared to be magnified by a black hole located around 90 billion light-years away. By studying the gravitational lensing effects, astronomers were able to learn more about both the black hole and the quasar. Despite these advances, there's still a lot that we don't know about black holes. One of the biggest mysteries is what happens to the information that falls into a black hole. According to quantum mechanics, information cannot be destroyed. However, according to general relativity, anything that falls into a black hole is lost forever. This apparent contradiction between quantum mechanics and general relativity is known as the black hole information paradox. Some physicists believe that the paradox can be resolved by developing a new theory of quantum gravity, while others argue that the paradox is unresolvable and that it points to a flaw in our understanding of physics. Another area of active research is the study of black hole thermodynamics. Black holes can act like giant heat engines, converting the gravitational potential energy of infalling matter into heat. This process is governed by the laws of thermodynamics, which state that entropy wins every time. However, black holes also seem to have a temperature which is inversely proportional to their mass. The temperature of a black hole is so small that it's impossible to measure directly, but it can be inferred from the behavior of the accretion disk. By studying the temperature and entropy of black holes, physicists hope to gain a better understanding of the fundamental laws of nature. Finally, there's the question of how black holes interact with their surroundings. For example, how does the material in an accretion disk interact with the black hole? How does the gravitational field of a black hole affect the surrounding gas and dust? And what happens when a black hole collides with another black hole? These are just some of the questions that astronomers and physicists are working to answer. Overall, black holes remain one of the most fascinating and mysterious objects in the universe. As our technology improves, we're likely to learn more about them. But they'll continue to challenge our understanding of physics and the fundamental laws of nature.